Joshua
and Keisha
from Math Ethics. How are you today, Keisha? Feeling a bit of stressful or anything like that?
Hi, that's already obvious, Joshua. But I know that God will help me because these past few weeks we're praying for the Advent wreath because his birthday is coming.
So, speaking of Advent wreath, that is a bit connected with our subject today.
Yep, Advent wreath is a perfect circle and it is a part of a connect section. So today we're going to discuss about connect sections.
The knowledge of conic sections can be traced back to ancient Greece. Menaechmus is credited to the discovery of conic sections around the years 360 to 350 BC. It is reported that he used them in his two solutions to the problem of doubling the cube. Following the work of Menaechmus, these curves were investigated by Aristeus and of Euclid. The next major contribution to the growth of conic section theory was made by the great Archimedes. Though he obtained many theorems concerning the conics, it does not appear that he published any work devoted solely to them. Pappus, who lived about 300 Anno Domini, furthered the study of conic sections somewhat in minor ways. After Pappus, however, conic sections were nearly forgotten for 12 centuries. It was not until the 16th century, in part as a consequence of the invention of printing and the resulting dissemination of Apollonius' work, that any significant progress in the theory or applications of conic sections occurred. But when it did occur in the work of Kepler, it was as part of one of the major advances in the history of science. In addition to these pioneers, there were many other mathematicians contributed to conics, such as Newton, Poncelet, Steiner, Dandelin, Dupin, Giorgione, Briantian, and Chasles.
I want to share with you some absolutely amazing geometric gems that really go back to antiquity. And these are based on just cones, and surprisingly, they're called connect sections. Because what we're going to do today is we're going to take a cone like this, and we're going to slice and dice it in different ways so that to reveal all sorts of hidden gems and which will lead to a wonderful, wonderful geometric structure. Now, we're going to use a double cone to visualize conic sections. To do this, we are going to cut our double cone at different angles. For the first angle, we are going to take a very flat plane which is at an angle of 0 degrees. When we cut our cone using this, we get a circular shape, as you can imagine very well that we are going to have a circle at every layer in the cone. Now, I have increased the angle of my plane a little. Now when I cut my cone at this angle, my circle has a circular shape does not remain anymore, and it has thread out of it to create lips. Now in the third situation, I am going to increase the angle of my plane further, and I have reached an angle such that this plane is now parallel to my cone. At this angle, when we cut the cone, the new shape we are now getting is called a parabola. Now in the fourth situation, I've increased the angle even further. Now in this situation, when I cut my double cone, you can see that both my cones are now giving you two independent shapes, and both of these together are called a hyperbola. So what we saw here was we can get 4 different shapes by the same double cone when we cut it at 4 different angles, and that is why all these 4 shapes are collectively called the conic sections.
But now I want to show you kind of geometrically what they look like, and you can actually describe these things by rules. So for example, a circle. Well, all of you know what a circle looks like. But let me now tell you how to think about a circle in a kind of more connected section way. It's actually the collection of all points that are equidistant from a fixed point. Now, that's a very fancy way of saying something. For the ellipse, an ellipse is a curve that is the locus of all points in the plane. The summus whose distance in from two fixed points and the foci, separated by a distance of is a given positive constant. The other one, parabola, refers to the plane curve which is mirror symmetrical and approximately U-shaped when oriented. And the last one, hyperbola, a symmetrical open curve formed by the intersection of a circular cone with a plane at a smaller angle with its axis that the side of the cone.
So with this piece of paper, I will gonna explain it to you how we can get the standard form of a conic section from its general form. So for you to identify where the general form or standard form is through its parentheses, just remember the standard form has a parenthesis. The specific equation here is an example of a hyperbola, since it's already clearly written from its equation. So as I solve this equation, I will gonna explain it to you how we can identify a conic section from its equation. So first, circle. If its two squared coefficient terms are equal to the other side. In ellipse, it is two squared coefficient terms of the same size. The parabola is only one squared term. So with this information, we can easily solve such equations with ease.
We see them every day, but we just don't notice them. They appear everywhere around in the world, and they can be man-made or natural. The application of conics can be seen every day all around us. Conics are found in architecture, physics, astronomy, and navigation.
That's it for today.
Hope you learned something.
Merry Christmas!
And Happy New Year!
Why are you so stupid? Stupid? Why are you blaming me? He had the microchip.
Well, she never called for help.
What did Agent 4 do? Nothing.
Wait! I was guarding our way out.
God, this is so stupid. Shut up and think.
Think about this. Kingman started this whole ordeal of conic sections when he had a problem building a home with dimensions subpar and a cube double the size but not the length. And so he passed this information to Menaechmus, who attempted to solve the famous problems of trisecting the angle, duplicating the square, and squaring the circle.
He first defined these as the intersection of a right circular cone of varying vertex angle, a plane perpendicular to an element of a cone. Then there came Apollonius of Perga, who consolidated and extended previous results of conics and gave them names: ellipse, parabola, and hyperbola, and used a double nut cone to better illustrate and define conic sections. Years later, Pappus and Proctus also provided many commentaries on their predecessors' works.
In the early 17th century, with Johann Kepler's discovery of the elliptic path of Mars revolving around the Sun, the four types of conic sections are officially named: circle, ellipse, hyperbola, and parabola. And now, in order to open the vault, we need the 4 microchips that contains the information in these 4 conic sections.
It is your mission to find and retrieve these microchips. Remember Ariadne's password, the general equation. Your mission starts now. Enhanced vision activated. Anomaly detected.
Ariadne,
code na microchip. Ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0.
Password accepted. A hyperbola can be defined as the locus of all points such that the difference between the distance of each point from two points known as the foci is constant. The standard form of a hyperbola with a horizontal transverse axis, or the axis on which the foci line lies, is x minus h squared over a squared minus y minus k squared over b squared equals 1, while a hyperbola with a vertical transverse axis is of the form y minus k squared over a squared minus x minus h squared over b squared equals 1. The center of the parabola is h, k, while the two foci found at the distance of c from the center in each direction along the transverse axis, where c is equal to the square root of a squared plus b squared. The eccentricity of the hyperbola can be found by c divided by a. A higher eccentricity makes the hyperbola steeper, whereas a smaller one makes it more curvy. The vertices are a distance of a from the center of the parabola in each direction along the transverse axis. The difference between the distances of any point from each of the foci is equal to 2a. A hyperbola also have two asymptotes. The asymptotes can be found by y equals k positive negative b over a times x minus h for a horizontal hyperbola, or y equals k positive negative a over b times x minus h for a vertical one. An application of this is the satellite systems that make heavy use of hyperbolas and hyperbolic functions. Using hyperbolas, astronomers can project the path of the satellite to make adjustments so that the satellite gets to its destination. Another one is the sonic boom shock wave that has the shape of a cone and intersects the ground in part of a hyperbola. It hits every point on this curve at the same time, so that the people in different places along the curve of the ground hear it at the same time.
You have the microchip, Agent 4. Just look for cover.
X squared plus y squared plus dx plus ey plus f is equals to 0.
Password accepted.
An ellipse is the locus of a point which moves in a plane such that the sum of its distances from the 2 points called foci add up to a constant. Standard form for an ellipse where its major or longer axis is horizontal is x minus h squared over a squared plus y minus k squared over b squared equals 1. If vertical, then it's y minus k squared over a squared plus x minus h squared over b squared equals 1. The center is located at hk, and the foci that are found at a distance of c from the center along the major axis, where c is equals to the square root of a squared minus b squared. The eccentricity of the ellipse can be found from the formula b squared equals a squared times 1 minus e squared, where e is eccentricity. A higher eccentricity makes the curve appear more squashed, whereas an eccentricity of 0 makes the ellipse a circle. The directrices are the lines x is equals to positive negative ae. The major axis is the length of 2a and the minor one, 2b. The sum of the distance from each point to each of the foci is 2a. The concept of ellipse can be applied in various ways. 1. The orbit of every planet is an ellipse, with the sun at one of the two foci. 2. The property of light emitted from a focus reflecting to intercept the other focus is exploited in whispering galleries, where two people stand at the foci of an arbitrary large elliptical room and can clearly hear each other whispering.
Enhanced vision activated. Anomaly detected.
Seconds later.
Okay, Ariadne, the code is for me. ax squared plus zy squared plus dx plus ey plus f equals 0.
Password accepted.
The geometric definition of a circle is the locus of all points a constant distance r from a point h, k and forming the circumference c. The distance r is the radius of the circle, and the point O equals h, k is the circle center. The diameter d is twice the length of the radius. The standard form for a circle with the center h, k and the radius r is x minus h squared plus y minus k squared equals r squared. Or, if the center is in the origin, the equation is simply a restatement of the Pythagorean theorem, x squared plus y squared equals r squared. The concept of circle can be used in the wheels on a car. The odometer in a car knows how far the car has traveled because it uses circumference of the circular tire. The information on the hard drive on your computer, or DC or DVD, is also stored in concentric circles.
Enhanced vision activated. Anomaly detected. Warning, security detected. Escape the area. Warning, security detected. Escape the area.
Ayan, deactivate code for me. Password. AX squared plus BY squared plus CX plus DY plus E is equal to O.
Password accepted.
A parabola is the locus of all points such that they are equidistant from a point known as the focus and a straight line called the directrix. The vertex is the midpoint between the focus and the directrix. An axis of symmetry is the line passing through the focus and the vertex of the parabola, while the lactus rectum is the segment with endpoints that pass through the focus and is parallel to the directrix. The equation of a vertical or horizontal parabola with vertex at the origin of the focus is at 0, positive negative c, and directrix, the line y equals fc, is x squared equals 4cy. If the focus is at positive negative c, 0, and directrix, the line x minus fc, the equation is y squared equals 4cx. If the vertex is at h, k, then the equation of the vertical parabola with focus at h, k plus c, and directrix, the line y equals k minus c, is x minus h squared equals 4c times y minus k. Horizontal parabola of focus at h plus c, k, and directrix, the line x equals h minus c, is y minus k squared equals 4c times x minus h. One of nature's best known approximations to parabolas is the path taken by a body projected upward and obliquely to the pool of gravity, as in the parabolic trajectory of a golf ball. The friction of air in the pool of gravity will change slightly, but the error is insignificant. Number one is the discovery by Galileo in the 17th century that made the cannoners to work out the kind of path a cannonball would travel if it were hurtled through the air at a specific angle.
Who are you?
I am agent number 5. I was sent here to give you guys a message. Unfortunately, something happened while you guys are gone.
Wait, where's Agent 1?
I don't forget about her. Let's watch the video.
We found the chip. By the time you're watching this, I could be dead already. But I must warn you that a lot of people are after it to vote, for its contents contain valuable information about our world. Hide it and trust nobody.
What the hell are you doing?
Don't move. I have the bolt and your friend.
Agent 5!
It's been a long time. Do you still recognize my voice? I've been quiet for a long time, and now I have to take back what is mine. Are you ready for the big show? I've taken your precious daughter.
Where is my daughter? What did you do to her?
Well, she's fine and well. Do you want to take her back? Okay, here's your daughter.
Mommy, I'm scared. Take me home. It's okay, sweetie. Don't worry. I'll do everything just to get you back.
I'll just send you the address and then meet you there. Just you.
Agency speaking. This is Agent C5. Can I help you? Stop. Nothing, great. What happened?
Someone I don't know. They know what it was. It's our family's treasure. The double knife. But they only have one piece of it. I want you to find the rest. Here's the key.
I assure you, Mr. Curry, you'll find all the hidden pieces.
What's up guys? Welcome to Math Wiki. So today's lesson is about the double nap cone and the conic sections. So what's a double nap cone? A double nap cone in regular English is two cones nose to nose with the one cone balanced perfectly on the other. To put simply, it's just two cones perfectly balanced. Each of the halves of a double nut cone is a nap. This is the general formula. So it is ax squared plus bxy plus cy squared plus dx plus ey plus f equals to 0. Next is a history of conic sections. So the topic of conic sections has been around for many centuries and actually came from exploring the problem of doubling a cube. T-minus wanted to build a tomb and said that the current dimensions were subpar and the cube should be double the size. but not the less. Many mathematicians of the time tried to determine a solution to the problem, but it wasn't until the idea came to Plato's Academy that it was solved by a mathematician named Menet. 360 to 350 BC, Menet was discovered the curves parabola, hyperbola, and ellipse. However, he did not use these terms. Instead of these terms, he called a parabola a section of a right angle cone, a hyperbola a section of an obtuse angle cone, and an ellipse a section of an acute angle cone. He found this by examining the intersection of a right circular cone of a varying vertex angle and a plane perpendicular to an element of the cone. Archimedes never published an entire work dedicated to conics, but he did publish several books that mentioned it. For example, Architecture of the Parabola, Conoids and Spheroids, Floating Bodies, and Plane Equilibrium. It is said that Archimedes described the different sections of the cones with the names, and Apollonius just built up that idea from Archimedes. Even though Archimedes is known as the great geometer, he extended the knowledge of conic sections through his studies and is most well known for his 8 books that contain 487 propositions entitled Conic Sections.
This is for you, Sir Nico.
First things first, the parabola described by a standard formula. Y equals ax minus h squared, and then add a k. That is nowhere to be feared. The other part is h, and that describes the center. X coordinate. Find the v, find the d, find the f. That's the vertex, the rectrix, and the focus. To find the d and f, you need to use a plus minus 1 over 4a. Focus on the inside, in the curve. The directrix is a line. I could teach this in reverse.
Conic sections. We already know the steps to ace that. Next test for sure. Conic sections. We're a total pro. We'll get on that next. Hard work and students list.
Next up is hyperbola. Looks like the parabolas. Once again, a formula tells us how to make them. X minus h squared over a squared minus y minus k to the second over b squared. You get 2 vertices by taking hk and adding and subtracting with the value of a. These hyperbolas, they get some asymptotes. Plus minus b over a is the slope. And use that and the center to find the lines of equation. Hyperbolas increase the lines approach them. We'll be the group number 3 with our name and bold. So put me on the list now, you've been told.
Conic sections. We already know the steps to ace that. Next test for sure. Conic sections. We're a total pro. We'll get on that next. Hard work and students list.
Circles, circles. Radius squared is equal to the square root of the difference. X minus h and y minus k. The center once again. Let's take it at h comma k. Add and subtract the radius from the center. It's easy.
The ellipse, how I love that. It looks like a circle if you squash that. This right here is the formula. To find C, use the Pythagorean formula. Subtract and add C from each and k. That's how you get the foci. Okay, now we're almost done with the song. So next time you hear this, sing along. We already know the steps to ace that. Next test for sure. Conic sections. We're a total pro. We'll get on that next. Hard work and students list.
Well. Where is my double knock code?
Are you blind?
done. Now, you can have your daughter back.
Lori! Are you fine? Are you okay?
Yes, I did.
나의 두 눈을 감으면 떠오르는 그 눈동자 자꾸 가슴이 시려서 잊혀지길 바랬어 꿈이라면 이제 깨어나
Day by day, as you walk through the streets, follows the flow of our lives, we always encounter the curves. The things that help us move on our day and give spices to our lives. Car wheels, Ferris wheels, balls, Earth's revolution, rainbows, MacDo's logo, and the twin arc in Japan. These are just some examples of conic sections. But how? When did it start? And what's the story behind this concept? The knowledge of conic sections can be traced back to ancient Greece. These are among the oldest curves and are the oldest math subjects studied systematically and thoroughly. Menaechmus is credited with the discovery of conic sections around the years 360 to 350 BC. It is reported that he used them in his two solutions to the problem of doubling the cube. It is when King Minos wanted to build a tomb and said that the current dimensions were subpar and the cube should be double the size, but not the length. Many mathematicians of that time tried to determine a solution to the problem, but it wasn't until the idea came to Plato's Academy that it was solved by the mathematician Menaechmus. He discovered the curves parabola, hyperbola, and ellipse. However, he did not use these terms. Instead, he called a parabola a section of a right-angled cone, a hyperbola a section of an obtuse-angled cone, and an ellipse a section of an acute-angled cone. The cone itself was a single nap cone in which the plane was perpendicular to the axis of symmetry of the cone. Following the work of Menaechmus, these curves were investigated by Aristeus and of Euclid. The next major contribution to the growth of conic section theory was made by the great Archimedes. Though he obtained many theories concerning the conics, it does not appear that he published any work devoted solely to them. It is said that he described the different sections of the cones with names, and Apollonius just built of that idea from him. Apollonius, on the other hand, is known as a great geometer. On the basis of his text Conic Sections, an 8-book series on the subject. The first 4 books have come down to us in the original ancient Greek, but books 5 to 7 are known only from an Arabic translation, while the 8th book has been lost entirely. Apollonius gave the terms parabola, hyperbola, and ellipse derived from the Greek words for ellipsis, parabole, and hyperbole. He also began to use a double napcone instead of a single napcone because it had a better use of defining the conic sections. After Apollonius was the mathematicians Pappus and Proclus, who are the reasons why previous mathematicians are credited with examining conic sections. They did this by providing many commentaries on their predecessors' work on conics in the 5th century. After these two mathematicians historians, it wasn't until the 15th century, around the era of Renaissance, that there was a revival in the interest of Greek culture and knowledge. With this era came the works of Johannes Kepler. In the year 1605, he was the first person to show the elliptic path of Mars revolving around the Sun. This new discovery fueled motivation in the study of conic sections. However, it dealt more with a focus on the mechanics and astronomy. He also claimed that the line and parabola are extreme types of a hyperbola, while the parabola and the circle are extreme types of an ellipse. In addition to these pioneers, there were many other mathematicians that contributed to conics such as Newton, Poncelet, Steiner, Dandelin, Dupin, Jurgen, Brian-Kahn, and Chaucelus.
Let's see if we can learn a thing or two about conic sections. So to start with, what are they and why are they called conic sections? You might probably knew a few of them already, either the circle, the parabola, or both. The conic sections are the circle, the ellipse, the parabola, and the hyperbola. But why are they called conic sections? Simple, because they are the intersection of a plane and a right cone. Before we go to each conic section, let's define first what a conic section is and what are its parts. When a straight line intersects a vertical line at a fixed point called the vertex and rotates about that fixed point, the surface obtained is called a double right circular cone, which consists of two cones that join at the vertex. The line that rotates about the vertex is called the generator, and the line that remains fixed is called the axis. A right circular cone has a circular base, and its axis is always perpendicular line from the center point of the base to the vertex. The perimeter of the base is called the directrix. The lateral surface of a right circular cone is called a nap. A double right circular cone has two naps, the upper nap and the lower nap, making it a double nap cone. For a plane that is not perpendicular to the axis and that intersects only a single nap, the curve produced is either an ellipse or a parabola. The curve produced by a plane intersecting both naps is a hyperbola. Each conic section has a unique or typical equation form. These equations can be rearranged in various ways, and each conic has its own special form that needs to be learned to recognize. Given a general form, conic equation in the form ax squared plus cy squared plus dx plus ey plus f is equals to 0, which is the general equation for all conics, or after rearranging to put the equation in this form, this is the sequence that should be kept in mind.
When a single napped cone is cut with a plane perpendicular to the axis of the cone, the curve formed is called the circle. This intersection is a closed curve, and the intersection is parallel to the plane generating the circle of the cone. A circle is a set of all points that are equally distant from the symmetry center, called the radius, and also a circle is a special type of an ellipse. The equation of a circle comes in two forms. The standard formula:
quantity of x minus h squared plus the quantity of y minus k squared equals to r squared.
The general form of a circle is x squared plus y squared plus dx plus ey plus f equals 0. Here are some examples of a circle. Plotting it on our double napped cone, this is the circle.
When a single napped cone is cut with a slanted plane, a curve formed is called an ellipse. This differs from a circle in that an ellipse does not have a constant radius. It has a radius that changes between an x radius and y radius. However, an ellipse has two focal points, which the sum of the length of both focal points to any given point on the ellipse is always the same. These are the equations of an ellipse. The standard formula of horizontal axis is x minus h squared over a squared plus y minus k squared over b squared equals 1. And for the vertical axis, x minus h squared over b squared plus y minus k squared over a squared is equals to 1. The general formula of an ellipse is ax squared plus cy squared plus dx plus ey plus f equals to 0. Here are examples of an ellipse. Plotting it out on a double napped cone, this is the ellipse.
A parabola is formed by intersecting the plane through the cone and the top of the cone. Parabolas can be the only conic sections that are considered functions because they pass the vertical line test. A parabola is the set of points that are equally distant from a focus point and a directrix. A fixed line. The standard equation depends on the axis of symmetry. These are the equations of a parabola. Standard formula for horizontal axis. Quantity of x minus h squared equals to 4a quantity of y minus k. Standard formula for vertical axis. Quantity of x minus h squared equals to 4p quantity of y minus k. The general formula for parabola is ax squared plus dx plus ey equals to 0. Here are some examples of a parabola. Pointing it out on our double napped cone, here is the parabola.
A hyperbola is formed when a plane slices the top and bottom section of the cone. The pair of hyperbolas formed by the intersection of a plane with two equal cones on opposites of the same vertex. It is a curve, specifically a smooth curve that lies in a plane, which can be defined either by its geometric properties or by the kinds of equation for which it is the solution set. These are the equations of a hyperbola. The standard formula of horizontal axis is x minus h squared over a squared minus y minus k squared over b squared equals 1. The standard formula of the vertical axis is y equals k squared over a squared plus x minus h squared over b squared equals 1. Then the general formula of the hyperbola is ax squared minus cy squared plus dx plus ey plus f equals 0. Here are some examples of a hyperbola. Plotting it out, our double napped cone. This is the hyperbola.
Dad!
Oh, my daughter, what's the problem?
I want to share this watermelon to all of you, but I don't know how to divide it.
Hey, here's a possible solution for this problem. So there are four possible divisions of this watermelon. The first slice is for dog Spiky and for Christelle. The second slice is for Papa. The third slice is for me. And the fourth slice is for my sister. And the remaining is for Mama.
Oh, what a nice idea, my son. I think this would definitely work.
Good day, everyone. So today, we'll discuss to you about the conic sections. But before that, we will tackle about its brief history. There are many great ancient mathematicians who worked onto the conic sections, such as Euclid, Archimedes of Syracuse, Aristeas, Menaechmus. The credit of discovering the conic sections is given to Menaechmus. Apollonius of Perga, who pioneered in the extensive study of this and gave special names to the conics. He wrote the Conics, which was antiquity's arrival treatise on the conic sections. However, let us focus on the contribution of Apollonius. Apollonius wrote about conics in his series of books simply titled Conic Sections. Apollonius' nickname was the Great Geometer. He was the first to base the theory of all three conics on sections of one circular cone.
What is a conic section? Conic section is a curve formed by the intersection of a plane and a double cone. When a straight line intersects a vertical line at a fixed point and rotates about the fixed point, the surface obtained is called the double right circular cone, which consists of two cones joined at the fixed point called the vertex. The line that rotates about the vertex is called the generator, and the line that remains fixed is called the axis.
There are four types of conic sections: the circle, the ellipse, the parabola, and the hyperbola.
What is a circle? A circle is a locus of all points in the plane having the same fixed positive distance, called the radius, from a fixed point called the center. The circle can be found when a double nape cone is cut horizontally by a plane.
Let me show you an application for circles in real-life situations.
The second conic section is the parabola. What is a parabola? A parabola is the locus of points x and y in a plane that are equidistant from a fixed point called the focus and a fixed line called the directrix. And how is it visible to the double napped cone? When the angle made by the plane to the vertical axis is exactly equal to the vertex angle, we get an open curve called the parabola at the intersecting surface of the cone.
We will now solve some situational problems involving parabolas.
third conic section is the ellipse. An ellipse is one of the conic sections that most students have not encountered formally before. Unlike circle and parabolas, its shape is bounded curve which looks like a flattened circle. The orbit of our planets in our solar system around the Sun happens to be elliptical in shape. Also, just like parabola, ellipses have reflective properties that have been used in the construction of certain structure. An ellipse is formed by cutting a three-dimensional cone with a slanted plane. This differs from a circle in that an ellipse does not have constant radius. It has a radius that changes in between an x radius and y radius. However, an ellipse has two focal points, in which the sum of the length of both focal points to any given point on the ellipse is always the same.
We will now apply the concept of ellipse to some situational problems.
The last conic section is the hyperbola. A hyperbola is the locus of all points in the plane. The absolute difference of whose distance from two fixed points, f and f sub 1, is a constant. As in the case of the ellipse, each of the two fixed points is called the focus. When the plane, not necessarily vertical, intersects both cones to form two unbounded curves, each called a branch of the hyperbola.
We will now give an example on an application of hyperbola.